I think now we can already start with the breakout sessions. And maybe, James, you just announce the timing and so on.
Yeah, sure. Maybe I can also just go like for 1 or 2 minutes again to over the exercise so that people, just to remind people. Yes. Okay. So again, we use the same notebook and we go to exercise 2. And so, yeah, so basically the exercise is about doing regression for adjusting to estimate the causal effect. And yeah, we have 5 questions here. And I think we go over the questions yesterday. So the main question would be basically the question C here, that you need to really implement the regression to get the causal effect. And here, just to save some time, I have a piece of code to run a quick regression in Python. So you can have a look quickly here. So you can use this stat model, and you first put everything into a data frame like this. And then you use the stat model to do regression with this syntax. So for example, you can do x plus f here. You can then fit regression. Okay, I hope this helps. And then for optional, you can also try to answer it once you finish the question C. You can also try to think about question D and E. So these are maybe a bit open-ended questions. And okay, again, we're gonna put you into breakout room. And
shall I open the breakout rooms now, James?
Yeah, that would be great.
Great. So see you then all in a couple of minutes back.
Okay, I think everyone should be back now. I will share my screen and start explaining the solution. Okay, I hope you can see my screen. Yes. Yeah, so maybe I should repeat, also can repeat like the objective again. Maybe I've gone over that a bit too quick. So I think the objective is that we want to estimate a causal effect from X to Y. And we have this data generating process, the SCM here. But if we know the true, like the underlying SCM, then we can read off the causal effect from the coefficient. So by multiplying the coefficient, like what Jonas mentioned yesterday. So here from X to Y, we have this part from X to D to Y, right? So you multiply from X to D is -2, and from D to Y is -1. So the causal effect is 2. So just multiply the coefficient together. And this works in linear case. For nonlinear, you may not be able to do this. And now the idea is that we have data we generate sample from this SCM, and we want now to estimate this causal effect. So we expect to be 2, so we want to estimate it. And then this is where the value adjustment set kicks in. So for example, if we regress Y on X alone, then you can see that we may not get 2 out of it, because because we have this backdoor path that open. So we need to find a set that such that we can get the unbiased estimate of causal effect. All right. And this is, I just answered question A. And question B, now there are 2 recipes that Jonas mentioned, and can we use it to find some value adjustment set. And one recipe, the easiest one would be to use parent set. So the parent of the variable that you want to estimate the effect. So here the parent of X is the set C and A, So C and A is the value adjustment set. And another recipe is to use backdoor, to use this backdoor criterion. And the backdoor criterion, we just want to block the backdoor path from X to Y. So here, set A alone, also a value adjustment set. And then using K alone, also a value adjustment set, because this also blocks the backdoor path. And then you can go on, you can use the combination of A and K, also C, A, K as well. And this is the value adjustment sets from these two rules. But this is not all the sets, because these two rules are sufficient. So these are like sufficient conditions. So you can actually, there are actually more sets that satisfy this, that are the value adjustment set, but it's not by these two rules. But these two rules are maybe the most common rules that you can use. And now the question is, so we have these sets, we want to perform it in practice. How do we do it? In the linear cases, we just need to do regression by adding the treatment that we want at X, and then add all the value adjustment set on top of X. Okay, so let's try. I don't know if I can run it. I should do this run it. So let's try the first one. Okay. Oops, sorry. I need to run this one first. Yes. Okay, the first one, I put X, C, and A. So now I get the coefficient of X, and this is approximately true. So it's good. And maybe I can first show you that if I use X alone, I shouldn't get the correct one, right? So if I use X alone, then I get the correct one. And I can try, let's say, this one, just K, and it's also a good one, K. Maybe try some other things. Okay. Sorry, maybe A and K first. This is also a good one. And maybe I try this X, F and K. So F and K here, which is not in the list of the set that we derive from the rules, but maybe this is also a good one, even though it's not the it does not satisfy this backdoor criterion, because the backdoor criterion you cannot use descendant of X. But anyhow, maybe this is probably the most. The last one would be the one that people usually do. So you put everything, like all the variables in, and hope that it will work. And in this case, actually, you cannot get the correct causal effect if you put all the variables in. So I think what you can at least learn from this exercise, that if you want to estimate causal effect using this regression, if you want to interpret the coefficient from regression causally, then you need to first, like if you know the graph, yeah, you need to have first the graph, and then from the graph you can select the set that satisfy these two rules, and then this will give you the unbiased estimate when you do regression. Okay. Yes, and I think I will skip the question D and E for now to save some time. But we can, if we have time later, we can also discuss about that. We can keep back to you on this.
Good. Thanks a lot for that. So maybe there's a question in the chat. The first one is, so when you mean good, you're saying the coefficient is larger, causality is stronger. So here, right, again, remember the true causal effect. We can read this off from the structural causal model. And this is using these, for example, this path formula. You can also look at the sort of the definition of the expected value of y under the intervention of x, and then take the derivative with respect to x. You can do the math. This takes you a few lines. and then you will see that this is 2. Or you use this shortcut that we mentioned, that you look at the coefficients on the directed path from x to y and you multiply them, and then you also get 2. So this tells us that the true causal effect from x to y in the example is 2. And now good really means that we get an estimate that is close to 2. Because as James showed, that if you just put in, for example, either no other covariates, you just regress y on x, or you put in all covariates, so you regress y on everything, and then look at the coefficient of x. These are not good in the sense that these estimates are very far away from 2, and in fact they are not consistent. So if you want to get the causal effect from this regression, you really have to use a valid adjustment set.
I'm sorry if I missed something. So what you're actually doing is that in the end, you're taking all variables and regressing them onto y, right?
Okay, can you say that again? We are picking what?
No, so you're basically, we're regressing everything onto y, right?
So in mathematics,
yes,
or like we would say, we regress y on something else.
Sorry,
right?
yeah.
So y is the response.
Yeah. So you're regressing y on all the variables.
Yeah, but this is wrong.
No,
this is
exactly,
wrong.
exactly. No, so what I wanted to get at was, in real life. So basically, when we have such a data set, I mean, we'll probably have to use all variables to get the regression, or how? So you're saying we should use the valid adjustment set to select specific nodes and then use them for the regression? Is that what?
Yes. So because it depends on your task. If you just want to predict y, if you want to regress to predict y in the future, then you can use all the nodes. Then you can just try to get the best predictive model as you like. But if you want to get a causal meaning in your regression coefficient, for example, in the one for x, then you have to be very careful. So then putting in everything is not always correct. And putting in nothing is not always correct either. So then you really have to think about the valid adjustment set. This is when you want to have a causal meaning in your regression. And the reason why you want to do this, for example, is to say that if you want the regression to work, if you now intervene on x, then if you just put in everything, then your regression might fail.
Sure. Thanks.
Yeah. So there's another question here. A good valid adjustment set allows us to adjust for confounders, backdoors, etc. Indeed. So this is the valid adjustment set. This is what they have to make sure, because these backdoor paths, these are the ones that mess up if you just regress y on x. Exactly.
Hi, bro. Sorry. Can I clarify what does causal meaning mean? So is it the intervention thing, and then you see the effect on the variable that you're interested in?
Yes. So this is again the definition of a causal effect is this expected value of y under an intervention on x, and then we take the derivative with respect to x. So this is the definition of this 2. So in this sense, the 2 is the correct causal effect, because this expression here, this is just, in our example, this is just equal to 2. And now maybe I give I'll give another interpretation here. So you have, if you like, you have a causal model, so a causal regression model in terms of x, in the sense that if you now intervene on x, you want this this model still be a good model. So you want still to be able to predict y under an intervention on x. So then you also need to have a causal model. So you need to have this coefficient 2 there, and not a coefficient of 1.2 or minus 2 or something.
Okay, thank you.
Yes. So there's one more thing that I want to mention, because this is really one tool how to get this causal effect. So you're saying, well, if someone tells you something about the causal structure, so knows the graph, for example, then you can use these tools to construct a valid adjustment set, and this you can use in the regression to get a good estimate for the causal effect. Now, in reality, of course, we do not always know the causal graph, and there's nevertheless something that we can do to sort of break all these backdoor paths. And this is something that we are very much used to. This is the idea of randomization. And here I would like to briefly discuss it, because I think it's actually quite a genius idea. So sometimes you're asked, what are your top 10 ideas in machine learning and statistics? And this is definitely in my top list. So what happens in randomization? So let's say we are looking at a study, and you know this from the newspapers all the time, of course, where you have a dependence between a certain treatment X and an outcome Y. So think about X again being a nutrition or some diet, and Y is the health status. Now, the problem is that this can be confounded, right? So maybe someone thinks about, so maybe it is that people who are doing a lot of sports, they tend to eat a certain type of food, and they are also more healthy. So if you want to estimate the causal effect from X to Y, so how much really does the nutrition or this diet contribute to the health status, then we have just learned that we have to adjust for this sports, so for this variable, for this confounder, because this is the backdoor paths. But now imagine a situation that in this, it's probably very hard to come up with all possible confounders. So maybe there are more confounders. Maybe this is like socioeconomic status, or maybe there's something related to your parents, how they treat you, or this could be a lot of different things. So now what randomization does, one way of looking at this is to say it breaks all these confounding paths at once. And how do they do this? So in randomization, we now randomize the treatment. So we take, let's say, 100 subjects, and for each of one, we throw a die and then decide, okay, depending on the outcome of the die, you either take this diet or another diet. And by doing so if you think back about the structural causal model, right, we are replacing the assignment of X. So no matter what X was before, no matter what went into this X, so into the decision what your diet was, whether it's sport, whether it's socioeconomic status, whether it's your parent, it doesn't matter. No matter what it was, we are replacing this now by something that only depends on randomness. So what happens, we are breaking all these incoming links, no matter how many there were and how they look like, we are breaking them in a randomized trial. And then this means that, well, if in this randomized distribution, which you can think about as an interventional distribution, if you then see a dependence between X and Y, then this really must be due to a direct causal link from X to Y. Or in other words, so in this randomized experiment, because there are no backdoor paths, I can just regress Y on X. So the empty set becomes a valid adjustment set. It's basically saying the same thing. So this is why randomization is, in my opinion, such a genius tool, because no matter what was confounding this effect first, we are now breaking it. And this is, of course, something that we are very much used to, because if you're a pharmaceutical company, you're trying to sell a drug, you have to go through these randomized studies, because it's just too uncertain if you're saying, well, we just put it on the market and then we'll see like who buys it and who takes it, and then we see whether there's a dependence, and then we try to correct for the confounders. This is what we believe is too uncertain, because it's very hard to list all the confounders. Yes, this is like a randomized control trial, just a different name for this. I just wanted to put this into into our language now. Okay, and now sort of just historically, this is an example that you may have heard about a lot. So this is this is a paper from the 50s. It's actually a surprisingly good paper, I think, about the dependence between smoking and lung cancer. Now, this was debated a lot. This was an important example. Why? Because the politics then said, well, if there's a dependence, we should put a tax on tobacco, for example. So they said maybe there's a causal link between smoking and lung cancer. And now the tobacco industry said, no, we don't believe that there's clearly there's a dependence. This is written, you can find this in this paper, it's very well analyzed. But this dependence is not due to a causal link, but it's due to a confounder. And now what shall we do, right? So we have these two tools available. So once we can say, well, we randomize smoking, and then just we see whether there's a dependence or not. And this clearly we cannot do because it's unethical. So there's no way we can randomize smoking, because if we think that it causes lung cancer, we cannot force people to smoke. Now the other the other thing that we can do is we can try to use this adjustment, right? So we can try to block all these backdoor paths. And this is also done in this paper. So they said maybe age is a confounding factor. So maybe old people smoke and they also get lung cancer. So they adjusted for smoke. They also adjusted for socioeconomic status. They adjusted for many different covariates. And now, what did the tobacco industry say? So you can maybe put yourself into the shoes of a person working for the tobacco industry. And I should say, unfortunately, there were some people getting really rich working for the tobacco industry trying to come up with arguments. But put yourself into the shoes of a tobacco industry and try to find an argument that somehow prevents you of putting some tax on smoking, in the sense that you somehow try to find an argument that the dependence is not causal. Just think about this for yourself for a couple of seconds. What could you claim? So what they came up with is they said, okay, yes, correlation is not causation. That's what they're trying, but we are already in a more sophisticated state here, right? Because we are saying, well, we can try to adjust for like these confounders. Indeed, what they came up with is this genetics argument. And why is this so genius? Or not genius, but why is this a clever argument? Because then this would mean that there is a confounder. So they said that if you have a certain type of genes, then you feel the desire to smoke, and you get more, you have a larger likelihood to get lung cancer. And this is such a clever argument, because this would mean that genetics is a confounder for smoking and lung cancer. And we cannot adjust for it because we cannot measure it. It was back in the 50s, so we cannot measure the genetic type of a person that easily, and particularly not during that time. So this means that somehow, okay, we cannot randomize and we cannot adjust because we cannot observe it, right? If you think about the code, if you want to adjust for a variable, you have to put it into the regression. This means in particular, you have to measure it. And of course, we know that this is a bullshit argument, because now we know that genetics doesn't work as easily as this. And also we understand, of course, this causal path much better. And there are a lot of good and valid arguments why this is really a causal link. But this is the argument that they did in the 50s also to buy off some time in order to prevent having to deal with this tax. And personally, I like this book here, Merchants of Doubt, that describes a bit like how the process of how science got involved into these questions, and also how academics, this is the idea, right, were working for some of these industries. It's also relating to global warming, by the way. So I think this is an interesting book to read. Okay, so now just one last comment, maybe. There's just to put things in perspective. I don't want to spend much time on this because there are a couple of questions we want to discuss. So even if you have a confounded effect, so let's say it's from smoking to lung cancer, and there are some hidden variables that you do not observe, even if you cannot randomize, do a randomized control trial, there's this idea of instrumental variables. And maybe you have heard about the Nobel Memorial Prize in Economic Sciences that was awarded, among others, to Joshua Angrist and Guido Imbens. This is partially due to their work on instrumental variables. What is the idea there? It's actually a bit older than their work, but they are building up on these ideas. So what is the idea there? So even if you have data that doesn't really come from a randomized control trial, so you do not fully randomize smoking, but you have some exogenous variable that influences smoking and not lung cancer, then you can still try to estimate the causal effect. And this could be something like putting a tax, because then you hope that the tax influences whether you smoke or not, but not directly whether you get lung cancer. So these are settings. So if you know that you have an instrumental variable, so if this requires background knowledge that influences the treatment but not the effect directly, then there are methods called instrumental variable approaches that you can use to estimate these effects. It doesn't have to be a linear effect, but there are some constraints that need to be satisfied. I don't want to go into details here, but this is just a setting where you can use instrumental variables. Okay, so now, for example, I just sum up maybe here. So what did we just discuss so far? So far, we were really in the setting of saying that you know something about the causal structure, and now we are trying to do inference. So the first, to summarize this, the first point is, if we are interested in IID prediction, so this was also one question that came earlier, right? So if you're just interested in predicting Y from something, then you don't have to worry too much about causality, at least for now. So then I would call this as an observational problem, and you just use whatever regression technique you want to use. However, if you are interested in a system's behavior under intervention, and I would argue we often are, then you have to worry about causality. We talked about the SCMs. These are these very little, like, if you like, computer programs that allow us to talk about observational distributions, interventional distributions, counterfactuals we didn't discuss, and they also entail graphs. Then we talked about adjusting. What was this for, right? This is if you're given the graph and an observational distribution, then we can predict what happens in the interventions. And so there was one question about yesterday. I think causality is rooted from holding all factors as constant aside from the change in treatment group, but I'm not sure. So what does this relate to, right? This, I would say, if you make this precise, this goes into the direction of adjusting, because you can, this holding something constant is a bit like you put something into the regression model. Right. And here we try to argue you cannot just you cannot adjust for everything in general. You really have to worry about what is a valid adjustment set. And intuitively, these are the ones that are blocking these backdoor paths, these confounding paths. Okay, then I just mentioned instrumental variables. They may help if they are hidden variables. And if you have a situation like this, this is just an expression that you can look up if you like. Okay, so let's see what are other questions here. Regarding this randomizing the subjects into different groups and then apply different interventions to different groups, I would call the whole process an intervention, right? Because you are taking the treatment that may depend, if you just in an observational study, right? So that may depend on other factors, let's say nutrition. Depends on a lot of different things, determine what I buy in the supermarket and then eat. But now you randomize and you're saying this treatment variable, this is just completely random. So I would say this is one intervention. I wouldn't say that I intervene on every subpopulation, but I would say it's just one intervention in the system to just make this a random variable. Okay, I think these questions are hopefully covered. Otherwise, just say that or just put them in again. Okay, and now in the last hour of this little tutorial, we would like to talk about this other situation where we don't have the causal structure. No one tells us what the causal structure is, and then the question is what can we do with it? Now, this we call structural learning or causal discovery. Right? We are just given data and we're trying to infer something about the causal structure. This is where I think a lot of fun also research starts, because there's one important thing to note. There's no free lunch also in this particular problem. So we have to make assumptions in order to perform causal discovery. Why is this? So now, having the language of SCMs, we can now even formulate this in a precise way. So the core problem is that there are different structural causal models that induce the same observational distribution. And I encourage you to try this out on a piece of paper. So just write down one structural causal model, let's say with X causing Y, and one with Y causing X, and they induce the same observational distribution over X and Y. And this is the fundamental problem of causal discovery. So if we are not willing to make any more assumptions, then we cannot learn causal structure just from observational data. Now, I would say that this is actually a common thing, right? Because also in regression problems, it's in a way it's the same. Because if we are not able to make any assumptions, regularity on the assumptions on the conditional mean, we cannot do regression either. So if the function is arbitrarily complex, then we have no chance of learning them from finitely many data. And somehow we are seeing by all these experiments, right, or all these impressive results from deep learning and other regression techniques, that apparently there is a lot of structure and a lot of regularity in real life. So the question now is, can we do the same in causal discovery? So what the field has been doing for many years, and this I mentioned yesterday already, it's somehow coming up with assumptions under which structure learning becomes possible. And these assumptions are quite diverse and quite different. So they are very different types of assumptions that you can make under which structure learning becomes possible. And then it's somehow, I would say, also a question of trying out in real life whether these assumptions make sense or not. And this is why someone asked about some of the causal discovery methods yesterday. This is why I would say that if you're presented with a method in causal discovery, you should somehow try to challenge a bit the assumption. So what is the underlying assumption that makes the causality identifiable? And then you have to see, okay, do I believe in this assumption? Do I think it's plausible? In which sense is this testable? In which sense is the method robust against slight deviations from these assumptions, and so on. So this is what I propose to think about in causal structure learning. So this is related to some of the questions I think also that were asked yesterday. Let me just check. Yes. Okay. So now, what are some of these assumptions? So one of the things you can assume, and I'm just mentioning this in words now, is to say that there was this D-separation criteria that I mentioned a couple of times. This is just the separation criteria in graphs. And now one of the assumptions that people have been exploiting is to say, and this is called Markov and faithfulness, is to say there's a one-to-one correspondence between D-separations in the graph and conditional independence statements in the distribution. Because if there's a one-to-one correspondence, and this is really an assumption, then what you could do is you can say, I'll take the data from the observational distribution and I perform conditional independence tests, and these tell me something about the graph structure. So this is just one type of assumption that people have been exploited over the years. And today we want to talk about one other assumption that we have been working on for the last couple of years and tried out on many real-world data sets, and this is related to invariance. I know I didn't move any slides. So I have a lot of yellow slides in this presentation. So these are the ones that I skip over. So if there's interest, I'm happy to share the slides. And the yellow ones are the ones that I don't discuss. I just leave them in any case. So I jump forward to this bit here. So we are still in the setting of causal discovery. And what are we trying to do now? So we are given some observed data set. And here we have one variable that we are particularly interested in, a response that we want to predict. And the other variables are, you can think about covariates. And now there's an underlying causal structure that we don't know. And in this particular case here, we don't want to predict or infer the whole causal structure, but we just want to know what are the causal drivers of Y. So in some sense, we are trying to infer a causal model for Y. So this is in some sense easier than estimating the full causal structure, the full causal graph. So here we are only interested in the red bit. So we are trying to find out that X2 and X3 are causal parents of Y. And this is a method that I would like to briefly describe. And then you're also going to work on this a bit in the exercise. Okay, find the direct cause of y. This is the challenge now, and we don't know the causal graph, and no one tells us some expert domain knowledge. Okay, so again, this is data that we looked at. This genetic data from yeast. We looked at many years ago, actually. And just to let you know, right? So if you just say, well, maybe I just look at the predictors with the strongest correlation, then this is an idea that does not work. So you can hope that they are causal, but this is usually not the case. So here in this data set, this is a pair of genes where you see that so this is gene expression levels here where the dependence is relatively strong. And this is not a causal relation. How do we see this in this particular data set? The biologists were able to delete this gene. So as on the first slide that I showed, so I'm going to show this additional experiment in a second. So where this gene on the x-axis is removed, and then the question is what happens to the gene on the y-axis. And this is the additional experiment that was performed. So indeed, the expression level of the X gene goes down, but the expression level of the Y gene doesn't do anything unusual. So there's no reason to believe, or there's no sign of a causal effect from the gene on the x-axis to the gene on the y-axis. Maybe not surprising, but this means that means, well, just looking at strong correlations just doesn't work. Okay, and now here comes the basic idea that we are discussing. So the main point will be to say that rather than focusing on prediction, we are again looking at this invariance principle that I mentioned earlier, namely the idea that if you intervene on a system in a certain part, then a lot of other parts will remain the same. And this principle we are going to exploit. So in a way, we are trying to focus only on invariance. So how does this work? So I'm showing you just one example here. So let's say the true underlying structure looks like the graph on the top. So we have one response and we have a couple of covariates, and we don't know that this is the causal structure. What we do have access to is data from two different experiments. So think about a blue experiment and an orange experiment. And so here you can see that a lot of the things are different in the two different data sets, right? So the marginal distributions are different, a lot of covariances are different, a lot of sort of conditionals are invariant. So there's a lot of difference in these two different experiments. But what we are going to exploit is the following. So if the experimental condition, they can change as much as they like, but if they don't change the mechanism for Y, then we can exploit this. And why is this? Because imagine that the experimental condition is like an intervention on the system, and you can intervene on anything that you like, but not on Y directly. Then this invariance principle tells us that, well, the way Y is constructed from X1 and X3, this is exactly the same in the blue and the orange data. And we don't know that X1 and X3 are the causes, but we know that the way Y is generated from its causes, this is the same in the blue and the orange data. So this we can now exploit. So how do we do this? So first, just to say again, right, what are we trying to achieve? So if in such a scenario you are regressing Y on X, then this doesn't give the correct answer, because here you will get like a model where all the covariates are highly significant. So this is like this prediction idea, right? So if you just want to predict Y, then that's good enough. You can do something like this. But if you want to find the causes, then this just performing a linear model is not good enough. Instead, we are proposing this, what we call ICP, where the interface is very much the same. So you provide the vectors of X, you provide the data for Y. And in addition, we are exploiting this fact that we have two different experiments. So you're just also providing a vector of containing of ones and twos, just indicating which observation comes from environment 1 and which one comes from an environment or experiment 2. I'm going to explain in a second how this works. This is extremely simple, but the output will now be different from the regression. It will now output indeed X1 as a cause and X3 as a cause. And now I'm going to explain what happens. And here we are going to exploit the invariance principle. Okay, so again, this method always works if we have an underlying causal structure that we don't have to know, but where the the experiments are somehow generated by different interventions. Again, we don't have to know what type of interventions and where they are, but they should not intervene on y directly. And why does this help? Because again, in this scenario here, the conditional of y given its parents, this will be the same in the blue and the orange experiment. So many things will be different. All the marginals might be different, but the one thing that is the same in the blue and the orange data set is the conditional of y given its parents. So what do we do now? Well, we don't know what the parents are, but we can try this out now, because we can just go through, let's say, all different subsets and always see whether the conditional of y given the subset is the same. So what does this mean? So let's say we are just regressing y on x2. Then we are going to see that this is not invariant. This is not the same in the blue and the orange data. And how do we see this? Well, if you just plot the data, so here we are plotted y against x2, and we have the orange environment and the blue environment, and we see that the conditional is not the same. And this is this you can see in the fact that the regression coefficients are not the same. So if you just do a regression in the orange data, you get a very different slope than in the blue data. So here we can say, okay, 2 cannot be the causal model for y, because the causal model should be invariant. 2 is not invariant, so 2 is not a good candidate. And this we try out with many models now. So you basically go through, let's say, all possible subsets, and you always check, do I find this invariance, yes or no? And you can think about the regression coefficient being the same in the blue and the orange data. And then you get a list. So we get a list of sort of all the sets, and we always know what are the candidate sets for the causal sets. And here we say that this is what we have just seen, right? For 2, we make a cross because this is not invariant. So this cannot be a candidate. This is not a good candidate for a causal set. However, if you regress y on x1 and x4, then you are going to see, aha, indeed, this is invariant. So this is a candidate for our causal set. And the same for example, if you regress y on x1, x3, x4, so this is also an invariant set. So this is also a candidate for our causal parents of y. So now what do we do with this list? So now there are a couple of opportunities. So you have a list and you have all the candidates for your causal models. I think this is already quite a helpful information. And now the question is, can we do anything with this list even further? And one thing that you can do is you can say, well, maybe you look at all the good candidates and you see, do they have something in common? And here you see that, aha, indeed, the variables 1 and 4, they appear in all the positive candidates. And then you can output 1 and 4 because you're saying, I'm not sure what the true causal model is, but I'm certain that x1 and x4 are part of this. So here this corresponds to just outputting the intersection of all the good candidates. And that's all what it does. So what do? We don't know anything about the causal structure, apart from that we have some heterogeneity in the data. So we have 2 different experiments. And now we are just trying to find invariant models. And the invariant models, they tell us something, because the causal model is invariant. The invariant models, they give us a list of good candidates for the causal models. And this is what you can exploit. And here, so maybe a couple of words. So you can also get guarantees for this. I'm not going into details here. But what we can, just a couple of words to say. So again, now here, this is resting on an assumption, right? It has to, everything in causal discovery has to. So what is the assumption here? The assumption is that we have heterogeneity in the blue and the orange data. Now, what you can do is you can try to challenge this now. So for example, what would happen if you don't have any heterogeneity? So if basically the blue and the orange data are basically the same. So let's say the biologist tells you, I did 2 different experiments, but in fact, he or she did exactly the same experiment, and there's no difference in blue and the orange experiment. So in this sense, this is a violation of your assumption. So what would happen here? So if these are actually exactly the same data set, so to say, or from the same distribution, then there's no heterogeneity that you can exploit. So what would happen is that everything looks invariant, because these are basically the same distributions. So you get like a yes answer for every subset. So this means that in this violation of our assumption, so to say, we get like everything looks like a causal candidate, and then you are taking the intersection over this, and then you output the empty set. So here the empty set really means I don't know anything about the causal structure. So like if you like, the empty set corresponds to saying I do not know. Personally, I think this is a good idea, or this is actually a feature of this method. If you think about this as generating interesting candidates, for example, for further experiments. So if you're saying, okay, I really want to find like the causes in the sense that whenever this method outputs something, you are certain that this is correct, then in some sense, it's natural that if you have a violation of the assumption and there's no heterogeneity, that then you don't output anything. Okay, are there any other questions? Or are there any questions, I should say? Yes, could you please give an example of how blue and orange data could be different? So, for example, here I indicated this, right? So imagine that that you have an intervention on variable x1 and an intervention on variable x2. So let's say you generate a structural causal model, and then you just generate data from this model, and this is your blue data set. And in the orange one, you generate data from the same structural causal model, but you intervene on x1 and x2. Now, the beauty of this is that you don't have to know where the intervention took place. So the method, in some sense, finds itself or analyzes itself whether there's enough heterogeneity in the data. Now, can we split the homogeneous data into multiple chunks randomly and try out this approach? I like this comment. We also thought about this. So you cannot do this randomly, because if you randomly split the data, then what you will happen is that what you will have is you will have exactly the same distribution in the blue and the orange experiment that you just artificially created. So then we are in the situation that I described above, and you're just outputting the empty set. So this doesn't work. You can be wondering whether you can do something like clustering, right? And here you can prove, I'm not going into details, but you can prove that you can do clustering as long as if you base your clustering on something that you are certain is an ancestor of a y, so comes above of y. It's not a descendant of y. And this is used in a couple of applications. So, for example, we looked at like fertility rates in different countries, and there we used, for example, continent as creating the different environments. So why is this? Because we said that if you really want to understand what drives the different fertility rates, what are the causes for different fertility rates, then this model should be the same in all continents. So a practitioner, even if this practitioner doesn't know anything about causality, I think that she would agree in the sense that, well, if you now find a model that is very different in Africa, in Europe, and in the US and in Asia, for example, then somehow it seems like you have missed something, right? Then it's not a causal model yet. So maybe you missed an important factor. So I think intuitively this idea makes sense. And mathematically, we are just saying, well, continent is not caused by anything else. Continent is really an ancestor of y. So you can use continent, for example, as different experimental conditions. And in general, you can always use variables or clustering based on variables that are known to be ancestors of y. Okay, there are a couple of good comments. Let me just take 2 or 3 more of them, and then we go into the exercise. Does it work with hidden variables? Also a good question. So if they are hidden variables, there's another nice violation of these assumptions as far as I presented them. Then indeed, you still get a guarantee. The guarantee will be that the output is not current. In the method I presented, the guarantee is that with large probability, the output is a subset of the causal parents. If you have hidden variables, then with large probability, the output will be a subset of the causal ancestors of y. And so you may not get the parents anymore, but you still get the ancestors, which I think is still, it's actually a nice robustness result, because the ancestors still have a causal influence on y. I read something where they were using noise to identify causality. Could you comment? Yes, so this is just very briefly, because this is a very different approach where you use simplicity. So this is again, we are trying to identify the causal graph from a distribution, and we are not using anything like invariance or different experimental conditions like here, but you can also use other assumptions, right? I mentioned this connection between dependencies and deseparations in the graph, and this additive noise structure. This is something that has been also exploited. This is yet another assumption, and this is really about an assumption about a simplicity of causal mechanisms. So I would like to not go into more details because it's really a different idea, but I mean, in the book, for example, we are trying to explain it. How do you deal with the situation where a potential cause x1 of y may potentiate another cause x2 of y? This is actually not a problem at all. So this is in fact this helps for identification. So here in the, I mean, it's now maybe a bit advanced, but in the right picture here in this orange figure, you can actually identify, or the output of will be x1 and x4, even if you don't intervene on x2. So an intervention on x1 is actually sufficient to identify x1 and x4 as the causes. And the reason is actually this direct connection between x1 and x4. So I'm just saying sometimes it's even helpful. Do we hit combinatorial issues if feature size increases using method above? Yes, we do. So this, of course, you don't want to do in practice, because here I suggest to go through all possible subsets, and this is very quickly infeasible. So we applied this method also to large data sets, in the sense that large number of covariates, like in this gene example, we have like 6,000 genes, I think. What you can do are a couple of tricks. So for example, you can go through like a feature selection step where you do it's called variable screening. So where you screen down the potential causes. So it's called variable screening rather than variable selection, because it suffices if you get a superset of the causes. That's already fine. So there are some of these tricks. There's also a lot of structure, by the way, in this table that I didn't talk about. So you can, of course, use shortcuts. So if you're just interested in the intersection, then these are sort of algorithmic shortcuts. If you know that the intersection is already empty, you don't have to test other sets, because then the intersection, because you have two accepted sets where the intersection is empty, then you just can stop, right? Because no matter what you do, the intersection will still be empty. So there are a couple of these algorithmic shortcuts that you can use, but indeed, I would say that you really have to screen down to, let's say, 10 variables first. I should also say, I'm not going to talk about this today, but we are working also on continuous versions of this, where you're not only looking at this subsets, but more at discrete versions of this, which I think is quite an interesting direction, because this is, of course, much closer to being implementable also in like other more complex regression techniques and so on. Okay, I think maybe I'll try to see whether there are more questions. Okay, maybe this one last, and then we go to the exercise. Can structural equation modeling also handle causal relationships? Yes, so I view this as really a causal model. So structural equation modeling, this allows us to talk about causality. So this is, for me, think about structural causal models. It's actually more or less the same thing as structural equation models. People use different names. Sometimes they make a distinction between linear or non-linearity, but it's basically the same thing as a structural causal model. And these are really just ways of talking about causality. This is a structural causal model is something that allows us to talk about interventions, about saying what is actually a cause. If you want to properly define this, you have to talk about you have to use the language of a causal model. And I really view these structural causal models as a tool to talk about causality and the problems. And this one I'm talking about now, this invariance principle, this is a method of solving one specific task in causality, namely, if we are given some data, can we infer the causal structure, but like the causal appearance of Y. But I could not even talk about the problem, I would say, formally, if I didn't have the language of a structural causal model, because then I'm like, what are all these graphs and what does it mean to be causal and so on? So I really need these structural causal models to even talk about this. Okay, so let me just hand over to James again, and then we talk about the last exercise.
Okay, thank you. Yeah, so let's go to our last exercise. I will just post the link once again in case that maybe there are new people joining. So you can find the link on this on the chat. Okay, so let me try to share my screen. Okay, I hope that everyone can see my screen now. So now we're going to do the last one, exercise 5, invariant causal prediction. And in this exercise, we're gonna see how we can do ICP in practice, and also to also get some more intuition about ICP. And I can go over it now. So let me just execute the code. And the first one we have this scatter plot between X and Y. And we have two environments, the observational and interventional environments. And the first question we ask is, so we have whether the predictor X is an invariant set, or roughly speaking, does the conditional distribution of Y given X are the same in both environments, in the observational and in the interventional environments. So you can try to guess here. And this is for bivariate case. And now the next question, we move to a multivariate case, where we have 3 covariates and try to infer the pairing of Y. And here, okay, this is not good. Why is that? Anyhow, I will move to maybe this one that I already executed. So here in question B, then so we gonna look at the scatter plot among all variables, and then look at another plot, which is the plot between the residual and the fitted values when we use each subset potential as the predictor. So for example, here we first we pull all the data together in 2 different environments, and then we fit one regression where we only use X1 as a predictor, and then we plot the residuals in each environment. And then we want to check whether, and then the question is whether we want to see which subset are the invariant subsets. So you can try to see in the plot which one invariant, in the sense that you can first think of is as in the bivariate case, like what does the invariant mean, and then try to use the same reasoning for the multivariate case. And the last question would be to, let's say we have a candidate of the invariant subsets. Can we then guess what would be the causal parent? And yeah, so I hope that it makes sense, and otherwise you can also put a question in the chat. Okay, So now what I'm going to do is, again, I will put everyone into a breakout room. So let me stop sharing. Okay, you also have this error. Okay, that's not so good. Okay, I will.
Can I ask, James?
Yes.
Is this error for both the R and the Python version?
Yeah, let me try the R version. Okay, I think for the R version it works. So I think okay. Yes, thanks for that. I think what we need to do, I will share my screen again. Okay, we need to execute this one first. I forgot that. So we need to, in the first one, we need to change from false to true first to download the data into the Colab. And then you should be able to do. So I think we just make it true like this, and then be fine.
Good. Can you maybe broadcast this? I think the breakout rooms are already open. And then,
okay, sure.
Okay, but then there's nothing in the way to start the exercise now, right?
Yes.
Great. Yeah, thanks.
Okay. Yeah, I think we are all back, and we can start. I can start the solution now. Let me share my screen. All right. So let's go over the first one. So from this plot, we can say that the conditional distribution, or the question whether the predictor X is an invariant set or not. And roughly speaking, we can check whether the conditional distribution of Y given X are the same in both environments. And here you can see that even though the marginal distribution of X are different, right? Because we shift the mean of X, but you can see that if we plot the regression line in both the blue or the orange sample, we will get the same regression line. So like this straight line here. So it means that the conditional distribution of Y given X stay the same across environments. And this is the idea of X being invariant. And indeed, because you can see in the SCM here that X is the parent of Y, and that's why X is invariant. And now we want to use the same reasoning for the multivariate case. So for the multivariate case, first we can look at the scatter plot here. And the main thing that we can look is a relationship between Y and predictors, different predictors. And here is still the bivariate case. And we can roughly see that for a single predictors, we don't actually see invariant because the conditional distribution of y given x1 looks different. Y given x2 also looks quite different, and also x3. So now we want to look into maybe not just a single predictor, but now a subset, some subset of predictors. And here we can use the same reasoning where we look at the, so now we look at different variable, but I mean, we can use the same reasoning. We look at the residuals and the fitted values, but we want to see whether the conditional distribution will stay the same or not. And here for x1, x2, x3, we can see that they are not the same. And for x2 and x3, maybe this can be a bit tricky because because it looks like if we condition, for example, if we look at the fitted value as 0 here, we will see that the distribution of residuals are different, and that's why the conditional distribution are the same. But now, if we look at here, for example, x1, x2, so even though we can see that like the marginal distribution of x may be different, that's why the fitted value are different have different range. But if we fix, for example, at some point here, we can see that the distribution of residual are the same. So for x1 and x2, this is an invariant set. And this is also the same for x1, x2, x3. And for these two, we can also see that they are not invariant. So the answer is that x1, x2, x3, and x1, x2. And if you want to use if we do ICP, then what we do is we have two options. We just need to intersect them, and the answer will be what would be the causal parent. The answer is x1, x2. And in this case, I think this is the correct causal parent. Okay. And optional, you can also here you can also try to run ICP code to check whether your reasoning are correct or not. And once you you can check it, and the ICP will also output that the estimated parental set is the set of 1 and 2. So this is the one ICP will return. Okay, I hope that makes sense, and I think we are running out of time, so I will just give it back to Jonas.
Yeah, thanks a lot, James. So maybe we just take the last few minutes to go over a couple of last questions. So this is one of the ideas that we have exploited over the last years, and just to finish this off. Now my computer is getting a bit slowish again, but I hope you can still hear me okay. So these are a couple of examples where we looked at this. So at this genetic data, you can indeed use this principle, even though you have about 6,000 covariates, to find causal pairs where you indeed then have you see a causal effect also when you do the gene deletions. So maybe I just go back a couple of slides. So this is how it looks like, right? So you find a couple of pairs, and then indeed, if you perform the experimental experiment where you delete the gene on the x-axis, you indeed find a causal link. So here, it really helps like to focus not on predictability, but on invariance. And you can see that the pairs that are now selected by this method are indeed satisfying this invariance property. So the regression lines are the same in the blue and the orange data set, or at least this is not rejected. And a couple of other examples so that you just get an idea. So there's nothing linear about this method, so you can also use it to nonlinear data. The different experiments, you don't just need to have two different experiments. You can also use time, for example, and ask the models to be invariant over time or space. And you can also include sort of the presence of hidden variables if the influence is simple. but maybe this is what I leave here. So there are a couple of examples, I think, where we tried this out in practice, and it seems to be working fine in the sense that it has this conservative component and is really only outputting something if you find an invariant model, and if not, that it just says I do not know what's going on. Personally, maybe a last comment. I think that this conservativeness is important in the sense that in prediction, so if you just have a prediction problem and you have a model misspecification, then in some sense you could argue, well, you can see this from the data because you can always hold out some data in a cross-validation scheme and train your method on the remaining data and then test it on the held out data set. And if your method performs, if you have a model misspecification that is severe, then you just see this because you will perform very poorly on the held out data. In causality, you cannot do something similar as easily because often we want to predict what happens under intervention. And if you don't have data available from this, then we cannot really use a similar cross-validation scheme. And this is why I think it's always quite an important feature to have if your method is robust with respect to these model misspecifications. Okay, so I just want to maybe finish this part here and talk a bit about the last questions that were raised yesterday. And I think we're also at the end of the time. So one question was whether we can apply causality in fact-checking domain. And this is, of course, I would consider this a research question. So causality has a bit of many people think that causality may play a bigger role in machine learning, for example, for their robustness issues or properties. And we are also working on this. Personally, I still think that this is an open research question. This also relates to the reinforcement learning question. So here you have an expert, namely James, who is working on this during his PhD. And indeed, we are seeing some scenarios where it may be helpful to use causal reasoning in reinforcement learning. And maybe I should say one more sentence about this. Reinforcement learning has already some causal component built in because these actions, if you like, this is like an intervention in the system and trying to find the best policy. So this means the best way of choosing an action depending on the state. This is in some sense already an intervention, so something causal. However, so how could causality still play a role? What we are seeing is that these methods sometimes have a bit of a hard time generalizing to unseen environments. And this is where many people believe that causality could come into play. So if you think about, I don't know, like learning how to play a computer game and then you go to the next level, then some parts of the policies you can keep and some other parts you have to adapt to the new environment. And this is something that usually humans are incredibly good at. And I think machines are not showing their full potential yet, and trying to understand like what are the things that we need to update. This is something that we are also working on. I think it's an interesting research question, but again, I would say this is current research. There was a question about whether we can briefly discuss the notion of invariant representation and causal inference. So what you saw here is in this ICP, it's exploiting the invariance for causal structure learning. So this is certainly one type of invariance that we see. And now, as I mentioned earlier, you can also try to think about whether we can use these invariances for trying to build models that are not necessarily causal, but robust with respect to changes in the environment. And here there's a close connection because you could say, well, all the invariant models are actually candidates for causal models. And therefore we can hope that they predict better in an unseen environment. And like a lot of the research that you see in this area works a bit like this. So instead of just focusing on prediction as like neural networks, classical neural networks or linear regression techniques would do, and also like instead of just focusing on invariance, which ICP would do, you're trying to find a trade-off. So for example, you're trying to look either for the best invariant model or the best predictive invariant model. So among all the invariant models, looking at the best predictive ones, or you can even try to find a trade-off where you're looking at the knob in between. So these are some of the things that we are working on. Now my computer is lacking very heavily because of this captioning. I don't know, this is I think a known bug with Zoom and Unix. But maybe someone wrote something into the chat that I cannot read now. But maybe someone can read something if there's a question that popped up. And otherwise, of course, we can also close. That is also fine. But if there's a question, a new question in the chat, maybe someone can just read it out loud. Maybe I can hear it.
I think I don't see any further questions in chat.
Okay.
Yeah.
Okay, but then that's all what we wanted to say. We can make the slides available in case you're interested in this. There are also the exercises. If you happen to be interested, there are a couple of more that we didn't have time to go through this tutorial. But that's really all what we wanted to say. I appreciated all the questions. I think that was quite fun, and I encourage you to keep that spirit, because that's really a great way to learn, I think. And there were many occasions where, now in retro perspective, I thought I should have asked more questions. So it's good that you don't seem to make this mistake. So well done. Thanks also, James, for the help here. And if there are some questions that pop up, of course, feel free to drop us an email.